All right, so just a few quick thoughts on the tangent line approximation, which is one of the major applications of the first derivative for single variable calculus. So again, that means, we've got one input, one output. We have the derivative function. Maybe we found it ourselves, or maybe we've been given it. And one thing we can do is approximate this function with the tangent line. So why we typically care about this is for computation time. If a function is really complicated, it's modeling some, complex physical phenomena or a social structure, something like this, it'd be better in small intervals instead of, let me kind of sketch this out. Say you've got some function doing something wacky and it has a relatively complicated formula, but we really only care about what's happening at this point, or maybe like, from here to here. Well, what we can do is come up with the equation of a line, which we'll call L, and this is what we call the linearization, or the tangent line approximation for f at this point A. And here's f of A. Okay, so it's this point that is on the curve, so we know this one specific value, but around that point, instead of talking about f of x is exact values, which might be hard to compute, we're going to use a line, which is very simple to compute because there's only so many parameters in a line, right? You just need a point and the slope. So this might be a good time to refresh ourselves on the equation of a line. And the one we're going to use, linear equation, is point slope form, which you've probably refreshed yourself on at this point, but if not, let's do it now. Point slope form in general is y minus any y value on the line equals the slope of the line times x minus another corresponding input value. So this is it in general, but for us, we care about one specific point, and that's the point that we're linearizing at, right? This isn't going to work, right? This line doesn't really work over here, so it's only got to work at the point that we care about. So we're going to call that A, x equals A. So at x equals A and f of A, we would use this. Y minus f of A equals the slope. I'm going to leave blank for a second. I want you to think about that. X minus A, so that's the point we care about. Now, what is the slope of this line? Well, the slope of this line would be none other than the derivative at this point, right? That would be the best use of the derivative because it is the slope of the tangent line, right? And that's exactly what we're doing. We're finding the line tangent to this point at x equals A. Excuse my voice this morning. So this is going to be f prime of A. That's my M. I'm going to highlight that here. All right, so that's why this is a major application, is because we're putting that specific slope of the tangent line to use. Okay, so let's do a quick example, and then we'll do another one after it that's a little more complicated. So here, let's find the tangent line to the function y equals x squared at the point 3, 9. Now, we might already kind of know the derivative for y equals x squared, but that is something we're going to need. So you think about, in order to do this, we're going to need really 3 pieces of information. For the parameter of a line, equation of a line, you need the input, the output. I flipped those over, right? This is input, output of where you're at, and then the slope. And here, this is the slope of the tangent line. So these two are simple because we've been given the input and output pair, so we really just need to find the slope of the tangent line at that equation, or at that point in time, excuse me. So for y equals x squared, find y prime. And so we'd go through the difference quotient, letting the time interval go to 0, of x plus h squared minus x squared all over h. And we've done this a few times, so I'm just going to kind of fast forward and let you know that we end up at 2x. Okay, so f prime of x is 2x. So then f prime of a then, well, what did we say a is? Well, a is 3. That's the point we care about here. Here's your a, f of a. So f prime of 3 then must be 2 times 3, which is 6. So the slope of the tangent line is 6 over 1. So maybe I should sketch out a little graph here to kind of correspond the two things. So what does the parabola look like? Something like this. Let me do that. Okay. So what we've done is said at x equals 3 and y equals 9, at that point we're going to take a line that's tangent to it. It's not a great sketch. Let me try that one more time. All right, I'll make it a little bit longer so we can see it. So here's this line L, which has its own equation, right? It is not necessarily, it's not a part of f of x outside of just this single point where they kind of, kiss or touch at the point of tangency. So here is, your a f of a, or your 3, 9. And then, the slope of this line is given by 6, so it's maybe got this mx plus b equation. Let's not confuse ourselves with that. Let's just put here that we know that m is 6 for this. Okay, so now to come up with the equation for L, we're going to use that y minus a equals f prime a x minus a. And this should be f of a over here. I'm going too fast, aren't I? Everybody see that? Okay, so this is my equation for the tangent line over here. And so I can plug in everything I know. I have this, I have this, I have this, and then I've got the equation for a line. So this will be y minus 9 equals 6 times x minus 3. Now, I think it's perfectly acceptable to keep this because I think it shows, hey, here's my point and here's the slope. But it's often acceptable to go ahead and solve for y. Adding 9 to both sides. And then you could get it to y equals mx plus b form. So this would be 6x, minus 18 plus 9, so minus 9. So either or are okay here. All right, and here's one more example. This one's similar to one of your practice problems. And it's asking to find the linearization of the function, which really means, using the tangent line approximation. They're kind of synonymous, but really it's, linearization means in a certain window, making a line look linear. Okay, so we're going to come up with the formula for the tangent line at x equals 1 for this function. Now, I'm not going to force you guys to take the derivative here, not quite yet. So I'll take care of that for you and assume, kind of as is the theme of this section, that we've come upon the derivative mysteriously. Okay, so let's say that you just happen to know that the derivative is given here. Okay, and I actually don't want you to compute that. But so we know the derivative is given here. We're at the point x equals 1. And so again, we're looking for that linearization, which is approximately f of x, is given by what we had before. So f prime of a times x minus a plus f of a, right? It's just solving for that y value. So what do we need? Well, we need f prime of a, we need a, we need f of a. All right, so we have x equals a. We actually don't have the height of the function or where we're at yet. So we need to go ahead and find that. So we know we're at x equals 1. You know, f of 1. Again, we're using this original function here. That's 1 cubed. We'll just write it all out. 1 squared plus 2. So this is 0 plus 2, which is 2. And we also need to know f prime of 1, aka the slope of the tangent line at x equals 1. And that's 3 times 1 squared minus 2 times 1 plus 2. So this is 0 plus 3 is 3. Right. So we've got everything we need. So this is 3 times x minus 1 plus f of a we said was 2. So we can simplify this to be 3x minus 3 plus 2 is minus 1. So this is the linearization of this function. So, you know, again, kind of what does this look like? Here's our f of x. It's this cubic function here. And so then at x equals 1, we're looking at this point here on the graph. So f of x equals 1 and f of 1 equals 2. So we know we're at this height. And then we know that the slope at this point is 3. And so let's see how good a job this does. So if we say, you know, maybe we'll use L. L of x equals 3x minus 1. And we see that this formula we came up with kisses this function very closely, you know, at a single point here. But it's a very close approximation. If we zoom in really close, right now here's, you know, 1.2 on the right, 0.95 on the left. That's a pretty good window where this line does a good job of approximating this function. Now, even in, you know, engineering, even in flying planes, designing planes, there's quite a bit of wiggle room in calculations. And so this is kind of pointing at that of how we can use calculus to simplify problems by zooming in on them, using limits, using the tangent line, to kind of get some wiggle room on error and discrepancy, and to really save us a lot of time. So I know this is kind of general because we're doing this on just graphs with little meaning or application, but this really does have a tremendous amount of application. All right, and so just to kind of summarize, that, you know, the tangent line to a, and I don't think I said this yet, differentiable function y equals f of x, so it satisfies the condition of being smooth and continuous at a f of a is given by this formula. And then again, we kind of use that same formula to find the local linearity. Means if we zoom in enough, around that point, f of x will start to look linear. And again, f of x needs to be differentiable for that to be the case. And lastly, that the tangent line approximation gives us the height and slope of the original function, and that it is the best approximation for the function at that point. Okay, so if you have another, the one way to think about this is, if you had another approximation for the function at that point that was linear, that this one would be better than that. Okay, no matter what you came up with. So it is kind of resting on, in the house of mathematics, in the rigors of proof, which we didn't really go through in this course, and that's fine. But just knowing that this is the best approximation for the function. All right, so I hope this is helpful, and we'll see you in the next one.